Hello and welcome to Applied Electromagnetics for Engineers. In this module we begin study of transmission line circuits in time domain. We want to understand how when I apply a pulse or a step voltage or some complicated voltage on a transmission line, then how would the voltage at the load side would look like in the time domain. So far what we have considered is the transmission line behavior in the frequency domain. Because we had applied a sinusoidal voltage, we had assumed that there were no transients in the circuit, all the transients had died down, and whatever that we were obtaining at every point, the voltage and the current both were sinusoidal. Okay. So this is what is called as the frequency domain analysis, or sometimes called as the steady state sinusoidal analysis. But frequently and these days increasingly digital designers are interested in how the transmission line would behave in the time domain. Why is it that they are interested? Because look at what the digital signals are. Suppose there is a IC module which is driving another IC, okay, and there is a wire between them, and so far we have seen that a wire is not just a wire but it acts like a transmission line. So there is a transmission line which is terminated by one IC, the driven or the load IC, and then there is a driving IC. The signals that are generated from the driving IC, this could be a NOT gate, this could be an AND gate, or it could be any other kind of a digital device. It could be clock which is changing and distributing the clock onto another chip. It could be the address decoder line, which is, or this is an address decoder which is actually trying to change the address or address a particular memory module or a particular chip on the microprocessor or on the microcontroller boards. So it could be any of these scenarios in which there is a digital signal which is changing in time, and it does not remain like a pulse. For example, if you are transmitting a pulse, it is not a pulse for all the time, it is a pulse for a finite amount of time, and then the value would again change. So it is necessary to, especially for digital designers, to understand how this digital signal is actually propagating on an analog transmission line. Okay. So the analog aspects of the digital voltages, how the voltage pulses are changing or how the step voltage is changing, is very particular and very important to minimize distortions and to better understand the propagation of pulses and propagation of transient voltages on the transmission line. In the power transmission line cases, there would be a momentary surge in the voltage because either the load has been momentarily short circuited or there was a lightning which struck the cable. So even though there the signal would be more or less a sinusoidal signal, there is also this surge or a transient that has happened because of the lightning, and one would like to understand how far this lightning would propagate or the lightning induced voltage would propagate before it would die down. So for all these cases, it is advantageous to work in time domain rather than in the frequency domain. Okay. Technically it is possible for you to work in the frequency domain by transforming everything into Fourier transforms or more easily into Laplace transform, but such an approach kind of masks what is happening in the time domain. So what we will do in this and couple of modules that would come now is to try and understand the behavior of step voltages first on resistively terminated transmission lines, and then extend this step voltage analysis onto a reactively terminated transmission line, and then finally consider how a pulse would propagate on a typical transmission line circuit that could be terminated either by a reactance or reactive element such as a capacitor or an inductor, or would be terminated by a pure real load. Okay. So let us begin by first understanding how a step voltage would propagate on a transmission line. Towards that, let me first discuss the problem with you, or let me first give you the basic idea of the problem. So we have some battery voltage. Okay. Any transient of some voltage can be modeled as a battery with some resistance. Keeping in mind the terminology that we have introduced in the previous cases, I am going to write the impedance or the internal resistance of the battery as Rg, reminding myself that G is the generator. So the voltage can also be written as Vg, just to show that this is the generator or the source. Okay. Now to this we connect a transmission line, or actually transmission line is already connected. If you want, you can think of this as a IC. Okay. So one integrated circuit module or one chip is this particular thing, okay, which is now equivalently represented by a voltage followed by a resistance. Okay. So, this transmission line of course is not intended, but it is actually the artifact of being a wire not being a wire actually. So, this would be, let us say, terminated in a load of some value RL. We will also assume that the transmission line has a certain characteristic impedance which is R0. Okay. Now, let us watch what happens. We will not connect this one to the transmission line. What we will do is we consider a switch, because when the voltage at the IC output or before the lightning, it would be some steady state voltage. Suddenly, because of an action, either the IC voltage line is changing, the address line is changing, the voltage would increase and then remain constant, or it would be of this form, or it could be of this ringing form. So, any kind of a voltage waveform is allowed. Of course, it is rather easier to analyze this case compared to these two cases, right. So, we will consider initially the idealized step voltage, which will be 0 before t equal to 0. So, if I were to draw the time axis, okay. So, this would be the generator voltage. So, this would be the voltage at the input terminals of the transmission line. So, initially this is 0, and the moment you turn on, that is turn the switch on, so the voltage jumps at this point, the voltage jumps to a value of Vg, okay, or rather the source will be connected. This voltage will not be exactly Vg at the input terminals of the transmission line. We will see what it would be. So, this voltage, but it is a change in the voltage, okay, and this is the switch that would be closed at t equal to 0. So, what we want to do is to understand what happens when the switch is closed, so that this voltage would now will be connected to the transmission line. Before connecting this voltage, we will assume that the transmission line is uncharged, that is, there was no remaining charges, and therefore, this transmission line was simply two wires which were completely inactive. Now, let me ask you, once I close the switch, do you think that this whatever voltage that should be available at the input terminals of the transmission line be immediately available at the output terminals of the transmission line? Of course, it will not be available at the output terminals of the transmission line, simply because it takes a finite amount of time for the voltage to reach from the generator side all the way up to the load side. And how much is the delay that is caused because of the presence of transmission line? That depends on what is the phase velocity of the voltage along that. I would like to remark that the term phase velocity is not a very good term over here, because phase would give you a connotation of a sinusoidal source, but there is no sinusoidal source here. So, rather than talking about the phase velocity, I should be more careful and talk about the delay that a particular point of the voltage or particular voltage value would take before it appears at the output terminals of the transmission line. Okay. So, that is the time delay of the transmission line, and I would like to actually talk about that, but occasionally I might slip up by using the term phase velocity, and that case you please correct yourself. Okay. This time delay is given by L by U. Okay. I will desist by writing this, desist writing a subscript of P for here, in the fear that I would be denoting this as a phase velocity. Anyway, so the delay is length by velocity, the velocity with which every voltage value moves on the transmission line. Okay. So, that is first thing that you have to observe or understand. The second thing that you have to understand is that when you connect the battery onto the input terminals of the transmission line, until the voltage that is connected here reaches the transmission line end or reaches the load, which will happen after a time delay of Td, there will only be a forward going voltage. Okay. So, from the time when the switch is closed and the generator is connected to the transmission line until the time delay Td, the source does not see the load. In fact, the source does not see the load until it goes here, and the voltage there will be, because of fact that RL will not be equal to R0, there will be a reflection. The reflected voltage would propagate, okay, and the reflected voltage would propagate and arrive at a time of 2 time delay. So, until the time 0 to t to Td, this load will not change or load will not see the voltage, okay, and from time 0 to 2 times time delay, the source will not see the voltage. Okay. So, the changes whatever that would happen, Rg would not see the changes. So, whatever the changes that has to happen has to wait for a total time delay of Td for the load to see the source, and for the source it would take a time delay of 2 Td. But once the reflected voltage reaches back the generator or the source, the forward going voltage is still present, so that is still propagating. But if Rg is not equal to R0, there will be further reflection at the source side or the generator side. So there will be a second reflected wave that is propagating, and that reflected wave would again be reflected from the load, come back after 4 Td, then again it keeps happening until you reach a site of steady state behavior. Okay. So in the steady state behavior you would see whatever the condition that would be necessary. So after all the transients have died down. Okay. How do we analyze, how do we understand the propagation of the step voltage here? There are various methods that have been followed to understand this voltage propagation in the transient or the time domain behavior. What I would like to just remind you is one simple fact. We started off when we discussing the transmission line theory or the solutions, we said that any voltage of the form f of t minus z by u should be the solution of the voltage equations. If you remember, for the lossless case, that was del v by del t, right. So del v by del z is equal to minus del I by del t with L, and similarly del I by del z was equal to minus C del v by del t, correct. So these are the time domain equations, and any function of the form f of t minus z by u or g of t plus z by u will satisfy this two set of equations. Okay. Therefore, these are the solutions. Now, if the source voltage is applied at t equal to 0 at z equal to 0, which is where the source or the generator is located for me. Please note the coordinate system here. Now, the coordinate system is z equal to 0 at the source side and z equal to L at the load side. Okay. So, when I connect battery to the transmission line at the input terminals of the transmission line at z equal to 0 and wait for a time of delta t, do I expect that the voltage change would have happened throughout the length of the load or throughout the length of the transmission line? No, the line would have been only charged up to a distance of delta t into u. Okay. So, this is along the z axis, it would have been charged only up to this u delta t, because there is a capacitance here, there is a capacitance here, there is an inductance here, I mean conceptually of course, not an actual way. So, each of these elements take some time to charge, and by time delta t only the section up to u delta t would have been, so this is z equal to 0, only up to the section u delta t would have been charged. This will continue, and at a time of t equal to Td, the entire section would have been charged, and this voltage when it sees the load would start to reflect. Okay. So, when the sees the load, it starts to reflect, and this reflected voltage would propagate backwards. Okay. So, there is a simple way to understand how this voltage propagation happens, and that understanding comes from what is called as a lattice diagram or the bounce diagram, okay, which is what is a popular method to understand how transients are propagating, and I would like to discuss that one with you. Okay. So, we are going to understand how the step voltage propagates by looking at a lattice or a bounce diagram. Let me first give you the construction of this. Okay. You get facilitated or you get understanding of how to use the lattice diagram, and once you have understood, if there is any discussion, if there is any doubt with regard to how the voltage would propagate, we can resolve them. First learn the tool, then we understand how the tool works for this particular case. Okay. So, the bounce diagram or the lattice diagram begins by first drawing two straight lines, okay, and these lines are labeled along. So, these lines are actually the time axis, okay, and the length between the two or the distance between the two will denote the source and the load points or the load reference planes on the transmission line circuit. In other words, this L is the length of the transmission line. Okay. So, this is along the z axis. Because there is a space and there is a time axis both on the same graph in which we are plotting, sometimes this is also called as a space time diagram. Okay. Sometimes this is called as space time diagram. Okay. The first step is to understand what is the initial voltage value that begins to charge the transmission line. So, would it be equal to Vg? Well, unfortunately that would not be equal to Vg because Rg is present. If the generator resistance were to be equal to 0, then the moment you connect t equal to 0, at t equal to 0 you connect the source to the transmission line, the voltage initially launched would be equal to Vg. Because there is Rg and because there is no characteristic resistance of R0, the voltage gets divided between these two, between Rg and R0 in an appropriate voltage dividing ratio. So, the initial voltage amplitude, let us call this as V1 plus, is given by, and this plus indicates that this begins to propagate from the generator side all the way to the load side. Okay. So, V1 plus will be equal to whatever the generator amplitude Vg that would be there times R0 divided by R0 plus Rg. So, when I write this, I am actually assuming that, or I am actually telling you that the initial voltage Vg that is applied, okay, through the resistance Rg sees a transmission line characteristic impedance. Okay. It will not see the load. Of course, it cannot see the load because first the V1 plus voltage has to go, reach the load, get reflected back, and only then the effect of RL would be visible to the generator. Okay. So, and because there is a 2 time delay of this happening, until that time this would be the valid transmission line circuit at the, or the equivalent transmission line circuit at the load, sorry, at the source or the generator point. Okay. So, initially we have V1 plus which would begin to propagate until a time delay of Td. So, we will denote that by writing down an arrow, okay, and this arrow reaches this point at Td. This is the time axis, please remember this is the time axis that we have written. On this I would like to mention what is the value of V1 plus. Okay. It is important that you mention the values so that when you add them up later on it becomes very easy. So, at this point it is V1 plus, but now what happens at Td? Well, you can't just have V1 plus and then the entire circuit stops. Unfortunately, because RL is not equal to R0, there will be an amount of voltage that would be reflected. How much would be reflected? First find out what is the load reflection coefficient from this expression, RL minus R0 divided by RL plus R0, and gamma L times V1 plus will be the one that is reflected. So, let us call this as V1 minus. This is our first reflected voltage. So, this V1 minus reflects and reaches the source at a time of 2 Td. Okay. And then this begins to propagate again. So, I will come back to this one what it is, but first let me write V1 minus which is equal to gamma L into V1 plus. You can also note down what is the value of gamma L here. Similarly, note down what is the value of the generator reflection coefficient. Why do I need this generator reflection coefficient here? Because once V1 minus reaches, you can think of this V1 minus as the source voltage that is now hitting this generator side. Okay. It is carried by the transmission line and it hits the generator. Because Vg is already sending out a positive voltage, when this V1 minus hits, you do not need to consider Vg. Okay. Vg can be considered as a short circuit. However, because of this reflection, there will be a reflected voltage back. So, what would that be? That would be V2 plus. Okay. This is the first forward wave, this is the second forward wave. By now you know what should be V2 plus. This would be gamma g into V1 minus. This would reach the load at 3 Td, which will then be reflected back by the load side with V2 minus given by gamma L V2 plus. Okay. And this again further reflects reaching here at 4 Td and so on until that would happen. Okay. So, this is the lattice diagram, and this lattice diagram contains all the information that is necessary for you to actually write what is the voltage at different points on the transmission line. Suppose I set up a hypothetical oscilloscope, well, not a hypothetical but a real oscilloscope. Okay. I set up this oscilloscope at the midway between the transmission line. Okay. So, the transmission line is of this length. I set up my oscilloscope at this point, okay, and I launch a step voltage here, right. So, now I am looking at the oscilloscope. Well, until half time delay I do not see anything. There is no change that would be happening until half time delay, right. If one TD is the one time delay, then until half the time I do not see anything, right. Where do I see some voltage? I would actually see some voltage because this is my oscilloscope, right. Oscilloscope is kept at L by 2, and any voltage that is launched from the source or from the load side would take about TD by 2 to reach the center of the transmission line. So, I will not see. So, if I keep moving along like this, so if I keep noting down what is this one I see at this particular time, which happens to be TD by 2, or rather TD by 2 in this case, the voltage continues to travel and reaches the center of the transmission line at a time of TD by 2, at which point the oscilloscope suddenly jumps and starts to show V1 plus, and it would continue to show V1 plus because any change to this voltage V1 plus at the center of the transmission line will not happen until this V1 minus comes and hits onto this, right, at which point the oscilloscope will now jump to V1 plus V1 minus. Okay. So, if I were to see this on the oscilloscope in terms of the time, okay, at Z equal to L by 2, I will not see anything up to time TD by 2, then I will see a jump of V1 plus that would continue until a time of, so what is the time here? This is TD has already elapsed, this is 1.5 TD. So, until 1.5 TD or 3 TD by 2, we will not see anything. At this point again I see a jump, okay. The jump will be having a value of V1 minus, okay. The jump will have a value of V1 minus, so that the total voltage at this point would be V1 plus V1 minus, okay. This is what would I see at Z equal to L by 2. Suppose I am interested in seeing what happens to the source, okay. So, the source is at Z equal to 0 obviously, right. So, initially when the switch is closed, the source voltage jumps up and it would be V1 plus, and this would continue to be V1 plus until it starts to receive a reflected voltage which happens at 2 times TD, right. So, when that happens, the voltage actually jumps up or down depending on the sign of V1 minus. So, the jump will be of the magnitude V1 minus, but would have a sign up appropriately. So, the total voltage at time 2 TD here will be whatever the voltage that has been launched. So, there is a change in here, that is V1 minus, but please remember, as soon as the voltage reaches, the voltage actually changes back to V2 plus. Therefore, here I misspoke earlier, the magnitude of the jump is not just V1 minus, but V1 minus plus V2 plus, okay. And this continues until you go up to 4 TD, at which point the jump would be of V2 minus plus V3 plus, okay. So, there would be another jump or could be a dip depending on whatever that you are looking at. This would happen at 4 TD, okay. So, this is how you would see at the source. Similarly, at the load, the total sum of the voltage here is 1 or rather V1 plus gamma L V1 plus, the voltage here will be V1 plus gamma L V1 plus V2 plus gamma L V2 plus, okay. So, this is the voltage at changes or jumps that are happening at 3 TD and at TD, okay. So, you can write down these voltages as a function of time and then actually set up an experiment in case it is possible for you to do so, and you can track down and observe that these are the voltage jumps that are happening, okay. Let us consider an example that would make lot of these concepts little clearer, okay. Let us consider the case where RL is about 100 ohms, okay, and R naught, which is the transmission line characteristic impedance, is about 50 ohms. I consider Rg to be 25 ohm, okay, and Vg to be about 10 volt. Now, let us try and find out what would happen to the space time diagram, and I would like to see what happens to the voltages at the source, voltages at the load, and voltages at the middle of the transmission line, okay. The first step is to calculate what is the value of the reflection coefficients. So, the load reflection coefficient is 100 minus 50 by 100 plus 50. So, this would be about 1/3, right. So, this is 1/3, and gamma g is 25 minus 50 divided by 75, this is minus 1/3. So, we have gamma L and gamma g differing in sign. Let us start with the lattice diagram. So, this is the lattice diagram that I would like to start. This is the z axis, this is z equal to 0, this is z equal to L, okay. Here I note down what is the value of gamma L, which is 1/3. I also note down what is gamma G, which is minus 1/3. Okay. What is the initial voltage amplitude that needs to propagate? Well, that is V1 plus. V1 plus is given by 10 volt divided between R0 and R0. So, this would be 50 plus 25. So, this is 1/3 of 10 volt. So, let me go back and correct this one. Instead of 10 volt, let me make it 9 volt, so that all the multiplication becomes slightly simpler. Okay. So, this would be 9. So, this would be 1/3 times 9, this is 3 volt. Okay. So, initially you launch a 3 volt 3 volt voltage step. Okay. So, V1 plus is equal to 3 volt. Okay. And this would reach at some time Td. I am not specified time Td. Once a voltage step of 3 volt reaches at time Td here, it would be reflected back. How much would be reflected back? 3 is the initial voltage times whatever is the gamma L value. So, that would be 1/3. So, this would be 1 volt. So, 1 volt will be reflected back, and then at the source side that it would again be reflected back at Td. How much would be reflected? Well, we started off with 1/3 3, this is what came in, or 1 volt came in, that needs to be multiplied by minus 1 by 3. So, this will actually be equal to minus 1 by 3 volt. Okay. At which point at 3 Td, when it reaches the source side, there will load side, there will be further reflection. This time it would be minus 1 by 3, which is incident, and 1 by 3 which is reflected. This would be minus 1 by 9 volt, and you can see whatever the other changes that are happening. You can see that the magnitude of the voltage keeps on reducing, because both gamma G and gamma L are less than 1. When you start multiplying these quantities, then they would start to go down to 0. Okay, gamma L into gamma G and so on, the product of that one will start to go to 0, and this change happens at 4 Td. Now we are ready to complete the problem. We want to sketch what happens at the center of the transmission line. Well, at the center of the transmission line, at half a Td by 2, or Td by 2, there will be a voltage jump of 3 volt. So, this is 3 volt. It continues to be 3 volt until we hit the next voltage value, which is a plus 1 volt at a time of 1.5 Td. So, at 1.5 Td we need, or we have a voltage which will jump by 1 volt. So, the total voltage will be 3 plus 1, therefore, there will be a jump of 1, this becomes 4 volt. Okay. And it continues to be the same case until we get to 2.5 Td. So, at 2.5 Td, what would happen? There will be a dip now, because 4, so this total voltage, the jump voltage is minus 1 by 3. So, this would be 4 minus 1 by 3. How much is 4 minus 1 by 3? That is about 11 by 3. So, which is, there is a 0.3 volt drop. So, there would be a small jump here. Okay. So, this is a small jump, not a very large jump. So, let me go back here and correct it. So, there is a small jump of about 1 by 3 volt, and it continues to remain as it is, and it keeps on, it just goes on like that. So, this is the voltage at L by 2. Now, what would be the voltage at the source side? Well, initially you started off with step voltage of 3 volt, which would persist. So, this is 3 volt at time t equal to 0, but at 2 time delay you would see that the total jump will be 1 minus 1 by 3. So, that would be 3 anyway is transmitted, 1 would arrive. So, there would be a jump of 1, but there would be minus 1 by 3. So, 1 minus 1 by 3 is again 4 minus 1 by 3 kind of a scenario. So, this would again this would be 3 plus 1 minus 1 by 3, this is 4 minus 1 by 3, which is 11 by 3. So, 11 by 3 is still slightly up compared to 3 volts. So, it would continue to be in this way, and when it goes to 4 times Td, this would be the case that would be there, but at 4 times Td you will now have a voltage of minus 1 by 9 coming in, and a voltage change of minus 1 by 3 into minus 1 by 9, which is 1 by 27 volt change. So, the total jump will be minus 1 by 9 plus 1 by 27. So, clearly 1 by 9 is larger in magnitude than 1 by 27. This can be approximately equal to 0. So, there is a small drop in the voltage, and then this continues to be as it is. So, this is how the waveforms would look. The waveform here would be same as the waveform here, except that this waveform would happen after a time delay of 2 Td, and I mean time delay of Td by 2. What I would now leave as an exercise is what would be the voltage at the load side. Again, you will have to add up the total voltage here. To that you need to add up the total voltage here and keep doing it, but you will quickly see that the circuits are kind of settling down to a steady state values, right. So, this voltage would be shifted to the load side and you would see some kind of a ringing effect. Okay. So, this is the transmission line which can be thought of as an underdamped transmission line. Okay. So, this is the example of using a lattice diagram in order to understand how a step voltage would propagate on the transmission line. In the next module, we will talk about more topics on this one. So, we will first consider terminating the transmission line with a inductive or a capacitive reactance, see how the voltage changes, and then we will consider the propagation of pulses. So, until then, thank you very much.